In this lesson, we'll talk about the inverse of a matrix. By the end of this discussion, you should be able to find the inverse of a matrix if it exists, use the properties of inverse matrices, and use an inverse matrix to solve a system of linear equations. We call from algebra and trigonometry, the additive inverse of a number is a number such that when added to the original number, their sum is 0. Meaning to say, this is the negative counterpart of the number. A plus negative a results to 0. Whereas the multiplicative inverse of a non-zero number is a number such that when multiplied to the original number equals 1. This is the reciprocal of a non-zero number, the multiplicative inverse. A times 1 over a is equal to 1. When it comes to the transcendental functions like trigonometric functions and inverse trigonometric functions, the sine of an angle theta in a right triangle is defined as sine theta is equal to the ratio of the opposite side to theta over the hypotenuse of the right triangle. The result is a real number. What if we are interested to find the value of theta? Then we use the inverse sine functions as follow. Theta is equal to arc sine of the ratio opposite over hypotenuse. Thus, the sine of inverse sine is equal to x, and the inverse sine of sine x is also equal to x for some values of x. Remember that inverse trigonometric functions are restricted to a particular domain. That's why I put here for some values of x. So, what do you notice on the relationship of them? They just cancel each other out, right? But always remember, the negative 1 symbol on the exponent is just a symbol for the inverse function. It does not mean reciprocal. Just like this one. When you say arc sine, this one doesn't mean that you're going to take the reciprocal of it, okay? This is wrong. So be careful. The concept of inverse functions can be extended to the matrices. Let A be a square matrix. The inverse of A is a unique matrix such that when you multiply A to its inverse will result to an identity matrix. Or when you multiply the inverse to the original matrix, the result will be the same identity matrix. This should be the identity matrix, where I is an identity matrix of the same size of A and its inverse. Always remember that we are only limited to square matrices. If the matrix is not a square matrix, then it doesn't have an inverse. If the inverse exists, then A is invertible or non-singular. Okay, that is the term when we have the inverse. It is invertible. By the contrapositive of this statement, if A is singular, then the inverse does not exist. Let's have the following theorem. Let A be a square matrix. A is singular or non-invertible if and only if its determinant is equal to 0. What are the examples of this? Suppose we have here matrix A with these entries. As you can see, the determinant of this one is 0. And what else? Let's say you have 3, 4, 5 here, and then 3, 4, 5 again here. The determinant of this one will also result to 0. Let's have the following theorems or properties for inverse matrices. If A is an invertible matrix, K is a positive integer, C is a non-zero scalar factor, then the inverse of A raised to K, C times A, and the transpose of A are also invertible. The following theorems also hold. The inverse of the inverse is equal to the original matrix A. The inverse of A raised to K, we can have here the K factors. Okay, we have the inverse times the inverse times the inverse until how many? K. And then we have here the inverse of C times A. We can actually take out the scalar factor here, but the scalar will be the reciprocal because the treatment of this one will be the reciprocal since it is a number. 1 over C times the inverse. Next, we have the inverse of A transpose. This is also equal to the transpose of the inverse. Okay? It's important for us to note this one. Okay? If A is an invertible matrix, then the inverse is also invertible. And then any power of the square matrix will be invertible as well, and the scalar multiple also, and the transpose of it. Let us have an easy example here. Find the inverse of the matrix B. Alright, from the definition, we have here A times the inverse. The result will be the identity matrix. Okay, what are we going to do? We can actually connect. Let us create a matrix such that the left part will be the given and the other part will be the identity matrix. Okay, we are going to perform Gauss-Jordan here. Okay, let's have the solution. Okay, this is the given. And then we will have the identity matrix here on the other side. Our goal here is to transform the left side. We are going to transform these to identity matrix. And then the right side will naturally be the inverse. Okay, what are we going to do? We're going to make this 0 using the Gauss-Jordan elimination or elementary row operation. So what will be the operation? We will have 4R1 minus R2. This will be the new R2. We have this one. It will not change because for the second row, we will have 0, negative 4 minus negative 3, so that will be negative 1, and then 4 minus 0 for this one, you have 4, and then for this, 0 minus 1, negative 1. Alright, the next that we're going to do is to make this 0. Okay, how will we do that? We may do R2 minus R1. This will be the new R1. Okay, for the first entry, 0 minus 1, we have negative 1, 0. 4 minus 1, 3. Negative 1 minus 0, you have negative 1. And then on the bottom row, it is not changed. Alright. For the first row, we're going to make the first entry positive and for the second row as well. So we are going to multiply negative 1. Okay, negative R1 will be the new R1. Negative R2 will be the new R2. Applying this row operation, we will now have the inverse actually. We now have 1, 0, 0, 1. And then negative 3, positive 1, negative 4, positive 1. Therefore, what is the inverse of matrix B? This. This is the inverse. Okay, we have -3, -4, 1, and 1. This is our answer. For 3 by 3 and higher order square matrices, we may use the following methods in finding the inverse. First, we have the Gauss-Jordan elimination, and second, we have the adjoint method. First method, by the Gauss-Jordan elimination, just like what we did in the 2 by 2 matrix earlier. Suppose that we are to find the inverse of a 3 by 3 matrix or higher. The Gauss-Jordan algorithm can be used to obtain the inverse if it exists. First, combine the original matrix on the left and identity matrix on the right in a single matrix. You may draw a line between them. So this is what we did earlier in the 2 by 2. Second, perform elementary row operation until the left side becomes an identity matrix. The right member is now the inverse of the matrix. First example, let us have here a 3 by 3 matrix. First, we're going to set up the matrix and then we have the identity matrix on the other side. Next, our goal is to make this 0. So, you have R1 plus R2 and 3R1 minus 2R3. Is that correct? Okay, let's have the transformation. We have here 0, R1 plus R2 only, 0, 5, 1, 1, 1, 0. Correct? We can actually draw a solid line here so that it will not confuse us. Okay, for the third row, 3R1 minus 2R3, we have 0. 12 minus 6, you have 6. And then 3 minus 4, negative 1. 3. Okay, and then here, 0, 0, 0. 3R1 minus 2R3, you have negative 2. Next that we'll have is this one. We have to make this 0. Okay, what will be our operation? We have 5 R3 minus 6 R2. This will be the new R3. Be careful. Okay, we have 0. And then 5 times 6, 30 minus 30, 0. And then this one, 5 times negative 1, negative 5 minus 6, negative 11. And then after that, here on the other side of the matrix, 5R3, 15 minus 6, 9. And then after that, 0 minus 6, negative 6. And then you have 5 times negative 2, negative 10. Minus 0. Okay, all good. We can make this positive 1 by dividing the third row by 11. However, it will be tedious for us to deal with fractions. So, let's just divide that later. Okay? Next, we are going to transform this into 0. Let's perform. Let's have the row operation for that. We have 11 R1 plus R3. This will be the new R1. 11 R2, same with the first row transformation. Okay, let's continue it here. 11 times 2, that is 22. And then here, 11 times 4, 44 plus 0. Next, we have 11 times 1, 11 plus negative 11, 0. And then on the right side, we have 11 plus 9, that is 20. Next, 0 plus negative 6, negative 6. 0 plus negative 10, negative 10. Next, for the second row, we have 11R2 plus R3. 11R2 plus R3, 0. 11R2, 55 plus 0. And then 11... Okay, this will be 0 because that's our goal, isn't it? Next, 11R2, 11 times 1 plus 9, 20. 11 times 1, 11 plus negative 6, positive 5. This one, 11 times 0 plus negative 10, negative 10. Okay, and the bottom row, nothing happened. Next that we'll have is the 44. We have to make it 0. So, we relate this to 55 here. There are both multiples of 11. So, we have 4R2 minus 5R1. This will be the new R1. Okay. 4 times R2, 0, minus 5 times 22. For this one, we have 110, negative 110. And then 0, and then 0. Next, 4 times 20, 80, minus 100. That will be negative 20. 4 times 5, 20, minus 5 times negative 6, so that will be 30. Correct? So we have 50 here. And then next, we have 4R2. Negative 40 minus 5 times negative 10, so that will be plus 50. So that is, you have positive 10 here. We are going to make the left side an identity matrix. So we're going to divide everything by negative 110. R1 divided by negative 110 will be the new R1. And then for R2, we divide all the entries by 55 to get the new R2. And for the third row, we divide by negative 11 to get the new R3. Right? Okay, we have positive 1, 0, 0. And then we have here, now we have our inverse. This is the inverse of the matrix B. Therefore, the inverse of the matrix B, we can actually factor out the 11. Okay? So, taking out the 1 over 11, using the matrix properties, the scalar property of matrices. So, we have 2, negative 5, negative 1, 4, 1, negative 2, negative 9, 6, and positive 10. This is now the inverse of the matrix B.